wait, here we have to do what you have to do here. You have to substitute in kilowatts. Since it is kVA is given in kilo, this also we need to calculate for kilowatts, or you can convert this into 5000 VA. Anything is fine. Okay, how much it will come? $5,000 into cos pi is 0.8 divided by 5000 into 0.8 plus iron losses. Iron losses given us 50 plus copper losses given us 150 into 100. Okay, how much it will come? Let's do the calculation. So it will come around 4000 divided by 4000 plus 200 into 100. It's around 4000 divided by 4200 into 100. 20 by 20 is 21. It's nearly about 95%. So our option will be D. Okay, in between some disturbance happened, sorry for that. I think some issue with the link. Okay, now we rectified. I will one more time I will explain the question. So based on the given data, we understood that the question is related to the calculation of efficiency of the transformer. Okay, so we note down the given data, but here we need to be very careful about the units. Why? Because here only we are going to do the mistakes. Some units are given in kilo, some units are given in watts. Okay, that means kVA is given as 5 kVA. That means we need, and iron loss and copper loss is given as watts. Either you need to convert this into kilowatts or we need to convert kVA to VA. Okay, after substituting the all given values, we get about 95%. Okay, without doing all this calculation, by seeing option itself we can solve. If you see the options A, B, C, D are almost different. Okay, not nearby. Some questions they will give 95, 97, 98 like that. Then you need to do the calculations. But here if you observe the options, these are all are the part away. Okay, so by seeing option itself we can select. How we can select? We need to remember the efficiency of the transformer always greater than the 90%. Okay, always greater than 90%. Whatever may be the losses, it need to be greater than 90%. Okay, so what is the best option in the given options is D only. By seeing option itself we can select, but sometimes if the values are nearby, that means 92, 93, 94 like that, then you need to do the all calculations. Is it clear? Okay, let's move on to the next question. The next question is about in TT connection the percentage tapping of main transformer and TZ transformer. Okay, first of all we need to understand what is this TT connection. The concept, what is the concept? What is the concept? The concept is TT connection. TT connection. TT connection, this is also called as Scott connection. This is also called as Scott connection. What Scott connection will do? It will convert 3-phase supply to 3-phase to 2-phase and vice versa and vice versa. That means 2-phase to 3-phase also we can convert. What is the application of this Scott connection? We are going to use in arc furnace and traction, electric traction. Okay, this is about the basic concept you need to remember when you are getting a TT connection. Okay, what is the importance of this card connection? That means if you observe this is converting to 3-phase to 2-phase, and the 2-phase is going to be connected to the arc furnace traction. That means unbalanced loads you are connecting. Even though loads are unbalanced in secondary, it should not disturb the primary. That means it should not disturb the main source of the supply. Okay, it should not disturb the main source of the supply. Why? Because along with this loads, so many other loads may be connected to the primary side. That means 3-phase supply, you are taking source from bus. No, the whatever loads connected to the bus should not affect because of this arc furnace or traction type of loads. That's why we need electrical isolation between the unbalanced load to balanced load. Okay, that's why we are going to prefer Scott connection, especially for this type of unbalanced loads such as arc furnace and traction loads. Okay, for that, how it is going to be occurred, we need to maintain the 3-phase system to be balanced. Only first point we need to remember is the 3-phase need to be maintained balanced. For that, what they did, they taken two transformers that are called main transformer and TZ transformer. These two transformers are connected such that to get balanced 3-phase voltage at the primary side. How it is get connected? Let's draw the diagram. Okay, this is about the Scott connection or TT connection. In this is called main transformer. This is called TZ transformer. Okay, why you need to connect like this means in order to get the balanced voltage. That means VA, VB, VC need to be balanced. Means what is the phase angle? VA at an angle 0 degrees, VB at an angle minus 120, VC at an angle minus 240 or plus 120. Anything is fine. Okay, in order to get balanced voltage at primary side, we need to make the connection like this. That means we are going to make TZ transformer at center we are going to tap the main transformer, whereas for TZ transformer we are going to tap at root 3 by 2. That is nothing but 0.866. Okay, it is 0.866 VP. Is it clear? So in Scott connection, to get balanced 3-phase voltages, we need to connect the primaries of main transformer and TZ transformer like this only. Then only you can able to achieve the balanced voltage. So from this diagram, what you understand? Percentage tapping. Okay, percentage tapping of main transformer. What is the percentage tapping for main transformer? It is 50%. Percentage tapping of TZ transformer is 0.86. If we convert it into percentage, it will be 86.6%. Our option is about A. Is it clear? Let's move on to the next question. The next question is about A single phase transformer has a turns ratio of 1:2 and is connected to a purely resistive load as shown in the figure. The magnetizing current as well as the load current drawn is 1 ampere. If the core loss and leakage reactances are neglected, the primary current should be, okay, the primary current should be what and all they are telling. They given the turns ratio. They are telling it is a purely resistive load. Magnetizing current and load current is given as 1 ampere. The core losses and leakage reactance, core losses, if you neglect, the primary current should be, okay. Let's note down the circuit diagram. Simple circuit diagram they given. We will write the equivalent circuit diagram here, okay. First we will write the secondary side. They are telling purely resistive load, it is taking 1 ampere of current, okay. It is taking 1 ampere of current. What about primary? This all leakage reactances and core losses are neglected, okay. It will be only shunt parameter will be there, that is x naught, okay. This will be the I naught, sorry, this will be the IM, this will be IM, this will be I naught, this will be I1 dash, okay. Let's take it as I2. This is the equivalent circuit for the given data. The magnetizing current they given as 1 ampere, okay. So in order to calculate the I0, we need to shift the parameters of secondary to primary. For shifting this, what we need? We need turns ratio. Turns ratio N2 by N1 is given as 2 by 1, okay. Turns ratio N2 by N1 is given as 2 by 1. So we know the relation between current and turns ratio is I1 by I2 equal to N2 by N1. Therefore, if you transfer the secondary to primary, what it will happen? This I2 equal to N2 by N1 into need to calculate I1, no? The current referred to primary side is going to given as N2 by N1 is 2, I2 is given 1, 2, it will be 2. Therefore, I1 dash equal to 2 ampere. Okay, let's redraw the circuit. This is load, resistive load, and this is the magnetizing component of a transformer. I shifted the secondary to primary side. It will be I1 dash, and this will be our magnetizing current I mu or IM. It is going to be 1 ampere. This is going to be 2 amperes. We need to calculate I0. This is our source. Okay, so I0 is a phasor sum of I1 dash plus IM. So if you want to find out I0 magnitude will be square root of 2 square plus 1 square. How much it will come? Root 5. That will be 2.24 amperes. Our option is C. Is it clear? So by seeing the question, it may be lengthy, but if you break down the question with the given data, and you can solve the question very easily. Once again I am telling, If you are strong at your basics, machines questions are very simple. Okay, to confuse the students, the examiner will give some twist inside the question. Okay, if you are strong at that basics, you can solve any type of questions in electrical machines. Okay, let's move on to the next question. The question is given about a single phase 100 kVA 1000 volt by 100 volt 50 Hz transformer has a voltage drop of 5% across its series impedance at full load. Okay, voltage drop of 5 volts across its series impedance at full load. This 5% for impedance drop. Out of this, 3% is due to resistance. The percentage resistance of transformer at full load for a 0.8 power factor lagging. Okay, what they are telling, that they given the voltage drops. Okay, they given the voltage drops due to the impedance. Let's note down the given data. Ez voltage drop due to the impedance is 5%, and voltage drop to the resistance is given as 3%. Okay, what is the formula? We know power factor. We need to calculate the voltage regulation at power factor 0.8 lagging. What is the formula we know for voltage regulation? Percentage regulation equal to ER cos pi plus or minus ER sin pi. Here, EX. Here you can substitute percentage R. Sometimes what they will give, percentage R they will give. Percentage R is nothing but the voltage drop due to the resistive parameter. Okay, due to the resistive parameter. So we can write like this also, the voltage regulation. So since they given it is lagging power factor, we need to write it as ER cos pi plus EX sin pi. Power factor we know and ER we know, but we don't know EX. We need to calculate the EX from the given data. We know that EZ square equal to ER square plus EX square. Okay, so EX square equal to EZ square minus ER square. How much it will come? 25 minus 9 equal to 16. Therefore, EX is equal to 4. Let's substitute the given data in equation 1. From equation 1, percentage regulation, we can get it as ER is 3, cos pi is 0.8 plus EX is 4, sin pi will be 0.6. Sin pi will be 0.6. By calculating this, we will get percentage regulation as 4.8. So our option will be A. Okay, is it clear? Let's move on to the next question. The next question is about which of the following statements is valid for transformers. Okay, we need to look into the different options and we need to validate whether these statements are correct or not. Okay, let's see. First option, in an open circuit test copper losses are obtained, while in short circuit test core losses are obtained. We already discussed copper losses. We need to calculate copper loss means the current flow need to be at full load current. Okay, the current flow need to be full load current or rated current. So in open circuit test, the current drawn is very small, that to meet the magnetization and to meet the iron losses. Okay, so this statement is wrong. And second, short circuit test, we are going to do the core losses. No, core losses we need to conduct at rated voltage. But in short circuit test, HV side, what you are doing? HV side, you are applying part of rated voltage. So these statements also wrong. So option A is completely wrong. Second option, in an open circuit test, current drawn at high power factor. No, we already discussed I mu is far greater than IW, this leads to the phase lagging by pi is near about 75 degrees. So it leads to the power factor cos pi naught will be 0.2 to 0.3. 0.2 to sorry 0.2 to 0.3. So in open circuit test the power factor is very less. So this option is also wrong. The next question is about in short circuit test current is drawn at 0 power factor. Okay, short circuit test the current is drawn at 0 power factor. 0 power factor, no, in short circuit test it may not be completely lagging by 90 degrees. Why? Because it is having both resistive and reactive parameters. We can't get ZPF. We can't get ZPF. So it will be around cos pi SC. It will be around 0.6 to 0.7. Okay, 0.6 to 0.7. So ZPF we can't get. This also wrong option. What about the last option in open circuit test? Current drawn at low power factor. Yeah, we already explained this. So the suitable option and valid statement is option D. Okay, is it clear? Let's move on to the next question. Okay, the next question is about a single phase transformer has a no load loss of 64 watts. Okay, obtained from open circuit test. When a short circuit test is performed with 90% of rated current flowing in its both LV and HV windings, the measured loss is 81 watts. The measured loss is 81 watts. The transformer should exhibit maximum efficiency. Transformer should exhibit maximum efficiency. Okay, let's look into the question. The question is about maximum efficiency. What is the concept behind this question? Maximum efficiency. From the given data, what we observed? No load loss at open circuit test. This is nothing but iron losses they given. Iron losses at rated condition. At the rate we rated they given. So it will be actual iron losses. And if you see the second one, the short circuit test is performed at 90% of the rated current. We need to understand. Okay, the copper losses whatever given is at 90% of rated load. What is that? 81 watts. And they are asking what to find out maximum efficiency at which load? That means X you need to find out. What is the formula we know? Iron losses equal to X square into full load copper losses. From this we can write X is equal to iron losses by full load copper loss. This is the formula we know. But in given data, okay, iron losses are calculated rated, so it will be as per actual. But the copper losses whatever is given is at 90% load, not at rated current or full load current. Okay, so we need to calculate the given copper losses to full load current. Then only you can able to substitute into the equation 1. From that we can get the that load rated current that part of rated current load X we can get. Fraction of rated current X we can get from equation 1. Okay, let's calculate the copper losses at full load. We know that copper losses at any load, at any fraction of load is given as X square into copper losses at full load condition. Okay. In short circuit test what they are telling, they conducted at 90% load. Then that fraction of rated current is 0.9. And losses, copper losses at 0.9 is given as 81 watts. Let's take it as equation 2. From equation 2, what you can write, 81 equal to X is given as 0.9, copper losses at full load. Copper losses at full load. From this equation, we can calculate copper losses at full load equal to 81 divided by 0.9 into 0.9. How much you will get? It will get 100 watts. Okay. Therefore, the full load copper losses is 100 watts. So, from equation 1, what is the equation 1? Calculation of maximum efficiency at fraction, at what fraction we are going to get maximum efficiency is given as X is equal to square root of Wi by Wfl. I given as 64. So therefore, maximum efficiency, we can write it as, therefore fraction of rated current at maximum efficiency is given as square root of iron losses are 64, copper losses are 100. How much you will get? You will get around 0.8. Therefore, X is equal to 0.8. The option is 80% of rated current. Option is 80% of rated current. Point is a fraction. If you write into the percentage in terms of rated current, percentage X is given as 80%. Okay, is it clear? Let's move on to the next question. The next question is about the best method to obtain the efficiency of two identical transformers under loading condition is. Under loading condition is, what they are asking, we need to calculate efficiency of two identical transformers under loading conditions is. Let's look into the options. First one is back-to-back test. This test is also called as Sumpner's test. Sumpner's test. What we are doing here in Sumpner's test, we are connecting two identical transformer back to back. Okay, then the secondary of second transformer is short circuit. Secondary of secondary transformer is short circuited. So in this, what is going to happen? Both iron losses and copper losses will occur at a time. Copper losses will occur at a time. That means, what it means, if you see, the first transformer is going to operate at a rated condition. So whatever the losses here is going to occur, it will be the iron losses we will get. The second transformer is going to be operated at rated current. So we will get here copper losses, here we will get iron losses at a time. So because of this, what will happen? So the heat rise, what it will leads to give? Heat rise. Heat rise you can calculate accurately. What is the need of heat rise? That means it will affect the percentage of transformation. It will affect the percentage of transformation kVA. It will affect the percentage of transformation kVA. That means indirectly it will affect the output kVA. Okay, so it will going to affect the efficiency. Okay, it will going to affect the efficiency. In Sumpner's test, what we are going to do? We are going to conduct at a time. We are going to conduct both open circuit and not open circuit and short circuit tests at a time. We will going to conduct. So it will leads to calculation of iron loss and copper loss at a time. It will leads to heat rise, thereby output kVA going to be accurately estimated and efficiency is going to be most accurate. Okay, so our option will be A. Let's look into the other options also. In open circuit test, we are going to calculate only iron losses. In short circuit test, we are going to get only copper losses. In no lead test or open circuit, both are same. Here also we can get only iron losses. So in other options, if you see, the iron losses and copper losses are separately calculated. That means the losses, how the losses are converting. The losses are converted in the form of heat. Okay, so the heat rise may be the not accurate if you convert separate. Okay, if you convert separate, we can't estimate accurately. Okay, so thereby our most suitable option will be A. Let's move on to the next question. The next question is about when a 50 Hz transformer is operating at 400 Hz, its kVA rating is. What they are asking, the given frequency of one transformer, and if the frequency is increased, what about the kVA, whether kVA will get increase or decrease. If it is increased, at what factor. Okay, let's note down the formula what you know. Okay, kVA is not directly proportional to V and A. Okay, kVA is directly proportional to VI. So that means kVA is directly proportional to V. We know transformer induced voltage, we can write it as 4.44 pi ft. From this we can write it as V is directly proportional to F. Let's take it as equation 1. Let's take it as equation 2. From 1 and 2, what we can write, kVA is going to be directly proportional to the frequency. Okay, therefore F1 by F2 equal to kVA 1 by kVA 2. What is the given data? Given data, F1 is equal to 50 Hz, F2 is equal to 400 Hz. Let's substitute the given data here. What we will get? Therefore, kVA 1 by kVA 2 equal to F1 is 50, Ft is going to be 400. Therefore, kVA 2 equal to 8 into kVA 1. Okay, that means kVA 2 is going to be increased by 8 times of initial kVA. So our option will be increased to 8 times. Option will be D. Is it clear? Okay, so it is a very simple question. If you write down the equations from your basics, you can solve the question very easily. Let's move on to the next question. The next question is about the possible kVA rating of auto transformer. I think in this question some data is missing. We will see it is later. We will move on to the next question. The next question is about star delta transformer. Star delta transformer, three-phase with respect to phase difference from primary to secondary. Identify possible ways of star delta connections. That means what are the different possible connections they are asking. So we know that in three-phase transformers we might have studied that based on the phasor diagram, it will vary. Based on the phasor diagram, there is a possibility of two type of connections. Okay, two type of connections, especially based on the secondary connections. Let's see what are the possible ways of star delta connection. First possibility is, let's write down the circuit of star delta transformer. This will be the primary phasors. This will be the secondary phasors. Let's take it as A1, A2, A1 and A2. This is B1 and B2. It has C1 and C2. Let's take that notation like this. Here it is A1, A2, B1, B2, C1, C2. The dot rotation will be here like this. The primary A1, A2, let's make it as neutral. Okay, based on the sense of connection, there will be two possibilities for delta. Okay, there is a sense of connection, there are two possibilities for delta. For suppose if you connect the delta like this, it will give one type of phasor diagram. Okay, this is the delta connection. Let's write down the phasor diagram. Let's write down the first phasor diagram of the primary. We need to remember always the tip of the phasor need to be either output or either input side or output side. So it will be A2, it will be A1. So next it is going to be connected to second phasor. This will be A1. A1 is connected to the B1. A1 is connected to the B1, so it will be B2. Okay, B1 is connected to the C1, it will be C2. Is it clear? This is the primary side phasor diagram. That means if it is a balanced supply, each phasor need to be displaced by 120 degrees. Let's note down the secondary side phasor diagram. While writing the phasor diagram, we need to remember that what we need to remember here, the tip of the phasor always towards the output side, and the thing is we need to the secondary phasor need to be parallel to the primary phasor. That means here this is the A phasor, this is the B phasor, and this C phasor. This will be the secondary A phasor, small a. Okay, how we need to write here? The tip will be A2 and the second tip will be A1. A2 is connected to B1. Okay, A2 is connected to B1. This will be like this and this will be like this. Okay, this will be the B phasor, this will be the C phasor. If we write the star network, connection of star network, it will be small a, it will be small b, it will be small c. Okay, it will be small c. If we take this primary and secondary phasors in a clock time or in a circle, what will happen? This is the primary phasor A. Let's note down the secondary phasor small a from here. Okay, small a here, what will come? This is the small a. If you represent these two phasors in a clock, what it will come? This will, let's take it is 2, it will be 1. Okay, it will be 1. What is the phase difference here? 30 degrees. Similarly, if you connect the second type of connection secondary, how we will get? It will be like this. Let's write down, this is primary, it will be secondary. Based on the sense of connection of delta, it will be vary. How it will vary? A to A1, B to B1, C to C1. Okay, So now this A2 is going to connected to B1, and this B2 is going to connected to C2, and this one is connected to A1. This will be A, B, C, and this will be neutral. A2, sorry, this will be A1, A1, B1, C1, A2, B2, C2, A2, B2, C2. Let's write down the first primary side phasor diagram. It will be A2, B2, C2. It will be A1, B1, C1 will be the neutral point. In secondary side, always we need to write the secondary phasor in parallel with the primary phasor. It will be A, B and C. What is the primary phasor? This is the primary phasor A, B, C. This will be secondary phasor A. I already told this phasor need to be, tip of the phasor will be A2, and this is going to connect it to B2. This is going to connect it to C2. If you write down the star connection from the given A, this one, what you will get? Let's write down it clearly. This is one phasor, this is second phasor, this is third phasor. This is A2, B2 and C2. If you convert the delta to star, it will come like this: A, B, C. Why you need to represent in star? To compare the primary to secondary phase displacement, both need to be either in delta or either in star connection. Okay, now we will represent these phasors. A phasors in a clock. So let's take reference as primary phasor A at 12. What is this? From this you can represent the secondary phasor small a as 30 degrees. Okay, so 30 degrees. It will be 11. This type of connection we can call it as star D1. This type of connection is called as star D11. Okay, the possible phase displacement is from, let's take it as figure 1, let's take is figure 2. The possible phase displacement is plus or minus 30 degrees. Okay, plus or minus 30 degrees. Option is 1. So they given A, B, C, D. So only possible option is B. Only possible option is B. Is it clear? So if you know how to draw the phasor diagram, from this we can come to the answer very easily. Okay, let's move on to the next question. The next question is about, given the following circuit with a transformer neglecting magnetizing current. They are telling magnetizing current is neglected. Okay, the following option is, so by seeing the circuit diagram, many students will get confused why the capacitor is connected. It may be difficult. Okay, it may be difficult to solve. Nothing is impossible if you are strong at your basics. If you see here the connection, that is a 1:1 transformer, that is isolation transformer. The impedance is, if you write it, is minus jXC. If you transfer to the primary side, it will be minus jXC only. Why? Because the transformation ratio is 1 only. So whatever the secondary is there, same impedance will be offered at primary side also. Okay, so if you redraw the circuit, electrical circuit, what it will happen? It will be the load L, and this will be minus jXC. This is the voltage phasor V0, and this is the voltage phasor V1. Okay, voltage phasor V1. Let's take current as I1. Let's take V1, we can take reference. Let's take V1 as reference, V1 at an angle 0. Let's write down from this how we can write, V0 is equal to V1 phasor plus, let's let this drop as VC phasor. Okay, from this what will happen, this V0 is nothing but phasor sum of V1 plus VC. What is VC? VC phasor is written as minus I1 into XC minus J1 into XC. Let's write down the phasor diagram. Let's take V1 as reference. V1 is at an angle 0. Okay, they are asking about two types of load, either it is lagging and leading condition. Let's consider it as lagging load. If it is a lagging load, the current will be I1 is going to be lagging. The current I1 is going to be lagging. We'll write down like this. The current I1 is going to be lagging. This is I1. Let's extend this phasor for some more distance. So we know that in capacitive load, it is a pure capacitance. Why it is pure capacitance? They told all other losses are neglected since we consider it as only capacitance. Okay, in a capacitive load, what will happen? The current, we know that in capacitive load, current leads voltage by 90 degrees. So this is the current phasor. Whatever the drop is going to occur here, it is going to be in 90 degrees with the current phasor. Okay, 90 degrees with the current phasor. So this drop is VC. So from this equation 1, the resultant waveform V0 is going to be drawn as like this. V0 is going to be drawn like this. Actually, it may not be exactly like this. It will be somewhat like this. Okay, somewhat like this. We'll redraw the circuit once. This will be the VC, this will be the V0. It will around near about 90 degrees. Okay, from this what you can say, V1 magnitude is more than the V0 for lagging power factor. Let's see about the leading power factor. Let's take the phasor as V1 as a reference, and for leading power factor means current leads the voltage by some an angle pi. Let's take it is I1 is leading. Okay, now what will happen? Let's extend this little more. I think this, if you compare like this, somewhere 90 degrees may come like this around. Okay, so the voltage phasor VC will be like this. So the resultant waveform V0 will be like this. Okay, this is for leading power factor. For leading power factor, what is going to happen? For leading power factor, what is going to happen? For leading power factor, V0 is going to be greater than V1. So our suitable option is D. V1 is be greater than greater than V naught for lagging power factor. Is it clear? Sorry. So our suitable option will be D. Okay, next going to the next question. What they are telling? A single phase transformer has a resistance of 1 unit, 0.1 per unit, 0.1 per unit, reactance 0.4 per unit, voltage regulation at 0.8 power factor lagging. 0.8 power factor lagging. We know that percentage, the concept is about percentage regulation. Concept is about percentage voltage regulation. What is the formula we know? Percentage voltage regulation equal to percentage R cos pi plus or minus percentage X sin pi. Okay, let's note down the given data. The given data is percentage R. Okay, here they mentioned it is in per unit, so percentage R per unit both will be same, that will be 0.1. Percentage X or X per unit will be 0.4, both will be same. Okay, don't get confused. Power factor is 0.8 lagging. Since the power factor is lagging, therefore the percentage regulation will be percentage R cos pi plus, we are going to take plus for lagging load, percentage X sin pi, what is that, into 100. They are asking in percentage, you need to be multiplied with 100. What is percentage R? 0.1 cos pi is 0.8 plus percentage X is 0.4 sin pi will be 0.6. How much it will come? 0.32 into 100. So therefore percentage regulation is equal to the 32%. Our option will be B. Is it clear? Let's move on to the next question. The next question is about, if an auto transformer is made from two winding transformer, given turns ratio is N1 by N2 equal to alpha. N1 by N2 is equal to alpha. Magnetizing current of auto transformer to magnetizing current of two winding transformer is, okay, two winding transformer is. They are asking about the relation between they given the data of turns ratio and they are asking the relation between magnetizing current. Okay, we will come from the basics. Don't get confused. First of all, we will write the two winding transformer relation. Okay, we know that I1 by I2 equal to N2 by N1. I1 by I2 equal to N2 by N1. From this, what you can write, I is inversely proportional to the number of turns magnet. So I1 is nothing but, at no load condition, most of the component will be magnetizing component. So Im is inversely proportional to N. So Im is inversely proportional to the N1. Coming to the auto transformer, what is going to happen? Auto transformer, if you see the diagram of auto transformer, same winding we are using for both primary and secondary. Okay, so if we are for suppose if it is a step down transformer, if we are energizing from here, what will happen? The total portion is N2. Here it will be N1. So the magnetizing portion will be N minus N2. Okay, N minus N2. Okay, N minus N2. So magnetizing component for auto transformer will be whatever the magnetizing current it is going to draw to magnetize this portion of winding only. This portion is N1 minus N2. Okay, is inversely proportional to N1 minus N2. Therefore, what is the ratio they are asking? Auto magnetizing current for auto transformer to magnetizing current of two winding transformer. What is this? How much it will come? N1 minus N2 divided by it will be like this, N1 divided by N1 minus N2. Let's take N2 as common. How much will come? N1 by N2 minus 1. We know N1 by N2 is given as alpha by alpha minus 1. So our option will be B. Is it clear? Okay. So from basics, if you are strong at basics, I came from the basics only. Okay, I derived the equations, and based on the requirement of our question, I substituted our given data, and we got the answer as B. Let's move on to the next question. The next question is about the full load voltage drops due to resistance and leakage reactance in a single phase transformer are 2% and 4% respectively. The full load copper loss is equal to iron losses. Okay, full load copper loss is equal to iron losses. The efficiency of the transformer at half load and unity power factor is. Okay, so they are telling us voltage drops due to resistance and reactance. They given percentage R. We know that percentage R is nothing but percentage full load copper losses. How we can represent? Percentage R is nothing but percentage full load copper losses in that but WFL of percent kVA. That means we can write it as percentage of kVA. That so percentage of full load copper loss which factor of S. Let's take S is equal to kVA of our transformer. Then how it will be? Percentage R is equal to, what is the percentage resistance they given? 2%. Then you have to write it as 0.02 into kVA. Okay, it is nothing but percentage copper losses equal to 0.02 S. Percentage 0.02 S. Okay. .02 and what they told, copper losses are equal to the iron losses. Therefore, WI is also be 0.02 S, where S is the kVA of the transformer. And what they are telling, efficiency of the transformer at half load. Okay, we need to calculate efficiency at half full load. So it will be 1/2 into S divided by into power factor is unity, so it will be 1 only. 1/2 into S into 1 plus copper losses is 0.02 S. Sorry, iron losses are 0.02 S. But we need to be very careful that they are asking at a half full load. So we know that copper losses at any fraction of load is given by x square into full load copper losses. Okay, so at half load means 1/2 into 0.002. So 1/4 it will become 1/4 0.02 S. Okay, 1/4 0.02 S. By solving this, how much you can get? You can get it percentage efficiencies at half full load will be around 95%. So our option will be A. So they given indirectly the copper losses. Sometimes the questions will be like this. Okay, the percentage R is nothing but per unit R or percentage R is nothing but the full load copper losses. The full load copper losses. How we can calculate? This is will be the percentage of the rated kVA. Percentage of the rated kVA. So we taken the first copper losses as they told. The copper losses equal to iron losses. We may for iron losses also we got from the copper losses, and we know the formula of efficiency. By substituting the given data, we got the answer. But we need to be very careful while substituting the copper losses here. While substituting the copper losses they are asking at a half full load. Is it clear? Let's move on to the next question. Sandwich windings are used in type of transformer. Okay, sandwich winding is nothing but first LV winding they will place on top of that HV winding, on top of that LV winding. Okay, like this they will do to reduce the sandwich winding generally prefers to reduce the leakage flux. To reduce the leakage flux. If you see, you might have studied in our transformer construction. There are two types: cell type and wound core type. Okay, in cell type transformer, what will happen? Leakage flux will be more. To reduce that, we are going to prefer the sandwich windings. In other spiral core or normal core or wound core, we are going to use concentric type windings. This might have studied in your theory classes. So our suitable option will be D. In cell type transformer, we are going to use the sandwich windings to reduce the leakage flux. Is it clear? Okay. We are going to wind up today's session by this. Okay, if you have any doubts, you can comment over the chat box. We are ready to help you. Okay, as you know, the notification may come very soon. Please speed up your preparation. Okay, the competition will be somewhat high. You need to be well prepared with previous year questions. Any competitive exams, if you are strong at previous year questions, near about 60 to 70%, almost all concept you might have covered. Okay, so we can complete the previous year questions of all subjects in upcoming sessions. Okay, so please support us. We are providing online coaching and offline coaching also, and test series also. If you have any doubt, we can contact